The positive number. Let us go below y because it's always a positive number. So that is always below the central. Okay, so we explained that in detail, and we mentioned that this value, the way you find it, you can either do double integration, the way I did it before, or you can, if you have a simple geometry, for example, in this case you have a tanker, and obviously the water is all the top, the level, and you see that there are forces on all four sides, right? And this guy that wants to design this tanker, he is only interested to find the force on this plate. For some design reason, he just wants to find the force on that plate. So for that plate, look at it. It's just a rectangle. How do you get that? Just table. Go to the handbook. For rectangle, you have simple relation for moment of inertia, and you can find. What if you don't have this in the handbook? If the geometry is complicated and it's not in the handbook, what do? You just go back to the last class, the way I did it. I took an element, and then I integrated the resultant force, and I integrated the resultant moment to get both the resultant force and the location. So, in fact, in your book, it creates one total section of like 10 pages for method of integral, and then he creates one page for method of like 5 pages for bent object, bent surfaces, and then he creates another 10, 12 pages for this case when you don't have bent geometry, it's just simple moment of inertia in the handbook. And then he sells you like 100 pages that he could just sell you like 5 pages of derivation of that integral. Not this, the integral method we did last class. You remember I did last class? I'm not going to develop the notes again because it was a lot of derivations. So if you just do integral, you can solve all these problems. It's the most general case. Alright? This is a special case. Now, once a problem with giving this class, or you use this formula, this one, and this one, and we find the resultant force and the location of the result. So the first problem, he says that, let me dim the light. He says that you got that line inside the spilled water, and then he wants to find the he wants to find the point P, which is actually the point of the resultant force. I mean, if you somehow compute with this formula the resultant force, it's going to act, this is central of this plate. It's going to act just a little below that, and it's going to push upward this way. Right? Find that. So find this distance going to the respective result, and also find the resultant force. So what it does is say, well, you have to have the information will have to do it. The density of water. These are something I knew. I want to tell you in the test if I give a problem like that. I may ask about double integration because it's in your book. It's not something that I'm making. It's just in your book. It's a part of the syllabus. Or if I give this and you have a limited time, I will give you all the formula like this. You don't need to memorize that. And also on top of that, I will give you the formula for moment of inertia. So I'm going to create in the appendix a table like this, that if you have the rectangle AB, so this side is A, this side is B, the moment of inertia about this axis called x bar, I x bar, or simply I bar, 1/12, A, BQ. I'm going to give this in the appendix for you. So you really don't need to memorize it. For the circle here, the moment of inertia I x bar, pi over 4, R to the first power. Things like that. And also for the triangle, also I give you that. I give you this formula. I give you this drawing. So if you can just simply understand the topic in class and practice homework at home, you you get 100 out of 100. Because I'm going to give you all this information. Right? So here he gives you the density, and also he starts with just finding just a simple thing. It says centroid is here, so the height, because you don't want to get this distance, you got to get the perpendicular distance, which is the height of point C. So that's what he does. He gets the height of that point, and then he substitutes the value in this formula. That's the first formula that I found. You put the values there, and then you get 1,000 for the density. This is the rho. You multiply by G. So if you get the density, this is not the density, you got to multiply by G, 9.81. And then you multiply that by H bar, which you got it 125, and then you multiply by area. That's the area. So all he did is just substitute values here in the formula, right? And you get the resultant force is 55 kilonewton. So 55 kilonewton. You remember when I said we have 5 steps, and we always want to make sure that we do verification. The last step, verify. Now, if you look at this geometry here, the geometry is the height of this canyon is 2.5 meters. So on 2.5 meter is like a little bit more like that. Here. So that's the height, and the base is obviously 1.5 meters. So this is a large anchor, right? So if you get the resultant force in one of the sides, that is like 10 newton. How much is the 10 newton? 10 newton is approximately, if you use F is equal to mg, or weight, WMG, and if you have, this is almost like 9.81, almost 10. 10, so M, the mass of the object should be 1 kilogram, which is 2 pounds. So 1 newton is a weight of object that is almost roughly 3 pounds. Right? It's not almost. And if you solve this problem with this, and you get like, what was the final answer? If you solve that and you get 55 newtons, don't go to the next problem. 55 newtons is not coming from this huge angle right here. Right? Something is wrong. Most likely, one of the unit conversion here, or when you do gamma, you gotta multiply that by G. You see the rho, this gamma is rho G. So the guy give you rho is equal to 2,000. Don't forget to multiply by G. You put this up in the formula of the gamma. Things like that. Always make sure that you verify. So next thing is to find the centroid. So look at it. He does a perfect drawing. The reason that I put the slides here, because if I do on board drawing of that, I certainly make perspective drawing errors, and that causes understanding. That will affect your understanding. So in order to you to perfectly visualize that, I create a slide, and you can see that this drawing, if you look at this from the sides, look at this plate, you see that. And you have this problem right here, that this is the center of the plate, just in the middle, or just the geometry center, C. And that's the point P, which is a little bit below that. Why? Because you have the trapezoid load. In this case, it's a rectangular load. Why? Because the gauge pressure at the surface is 0, right? So you see that the atmosphere pressure, look at it, the atmosphere pressure is what? Everywhere, right? So there is a P0 here and P0 here, and they're going opposite, so they cancel out. So the net result is the pressure coming from water, which is called gauge pressure. That's the reason you have that. In my derivation for that formula in the previous class, we assumed that the other side was vacuum, but the result is exactly the same. The result is exactly the same, because what? The gauge pressure is in both sides here. So he just goes ahead and substitute that in this formula. So y bar is just a centroid. So you put here y bar 1.5 in the middle of this plate, And you can see that when we move the middle of that. And then I bar is 112, it goes to the appendix, and you see the formula here, 112, AB squared, AB cubed, divided by A times Y bar. This Y bar and this A. And I get 2 meters. So what's the shift? 50 centimeters. You see, this distance is 1.5 meters to the centroid, and this point shift between the centroid and that is 50 centimeters. 50 centimeters plus 1.50 centimeters is 2 meters. So the shift is 50 centimeters, right? And he also compute X bar. What is X bar? I got Y bar. Look, if you look at the drawing that I made last class, this shape, if it's not symmetric, this arbitrary potato, it's an arbitrary shape, plate you have, right? If it's not symmetric, then you expect that the same shift that you have in the Y is going to happen in the X. So if this shape is like that, you're going to move a little bit to the right because you have more area here, right? So it's not X bar, it's X bar plus some shift. And if you draw the relation for that, just like I did last class, I'll give it a homework, you get X bar, the X locational center, plus a shift. And this shift is I bar XY. What's I bar XY? I bar XY is double integral XY dA over area. So we had I X bar was simply double integral Y squared dA. Now double integral, you should gotta have the square of distance. If for distance you use the product of x and y, you get ixy. And this is for symmetric shape, as we have in vector aesthetic, this is 0. So if your shape is symmetric, is it symmetric in the x? Let me bring the drawing here. Do you think it's symmetric in the x direction? If you put the axis here, is it symmetric about that axis?
Yes.
Yes.
Yes. So this result is immediately ix bar 0. Because you go to positive x and negative x, and you integrate over exactly the same thing. So plus minus the same exact value is 0. Right? So what he says, he just wants to do this problem in general case. So he said, well, I'll just get the value in the formula, and then he gets 0, because his axis, you see, is going passing through the center. 0 plus the shift, and this is already 0. 0 divided by y bar a, which is 1.5, plus 0 divided by 1.5 is 0. So it is 0. So all that matters here is the distance between the centroid and point P below it in the y direction. You don't care about x. It's perfectly symmetric. People even say it before even doing mathematics. So next problem is this problem. It says we have this container filled with a fluid, and find the magnitude and location of the resultant force acting on the end, the triangle on the end. Again, we have 1, 2, 3, 4 sides, and all sides, as a homework, you can go home and find the resultant force in this side. But for this problem, we said find the resultant force acting on this end of this plate, right? And the container is filled with the curve, right? So before you do that, you need to have again some information. Once again, you don't need to memorize anything. The formula for this, the I bar with the respective center of the triangle is all given in the appendix. So you go to the last page and you get the formula for that. You need the other density of the kerosene. The density is also given to you. So that density is 814. So you get gamma multiplied by 10 or 9.81. So that's the gamma resulting in the formula, right? So the next thing you need to do is to find y. If you want to just, sometimes I just say find the resultant force. Do not find the shift, right? Just get the resultant force. All you need to have gamma h bar a, right? You have a gamma. What's the h bar? H bar is the height with respect to the centroid. right? So we compute h bar. The entire height is 2 meters, 1 bar by 1/3. So that's the h bar. You substitute into that formula. Well, this is all in the book. If you want to take a photo of that, this problem you don't need to take it for a while, because these problems are both in the book and also I upload in the module section in the slides. So for this problem, I see that some of you guys will scan the whiteboard. For this problem, you don't need to scan it, it's in the book. Right? So you multiply that, you get y bar, and then if you want to get resultant, you down here basically you get h bar. You want to put it here, gamma, which is 7985 multiplied by that h bar, and then multiplied by area. Now for area of the triangle, we always forget that 1.1 half. Right? So this same vector static, mechanics of material, all the classes I teach, the structure and analysis, and I'm pretty sure here in this class, you guys do everything correct except the area of this triangle. If you're good, you forget 1.1 half, 1/3. Don't do that. Please double check it, make sure you don't get that 0.5. So that's good. 5.3 kilonewton. Again, you go back to it, well, that's a large tank, 2 meter height, a little bit more than me, right here, and the length is 1 meter. And coming from all that fluid, it's got to be something kilo. So that's a kilo. I'm good. If you get newtons, you have to double check. Right? Now, to compute y, p, the y location of that force, you just substitute in this formula. Again, you put y bar, which you compute it here, and then you add it, the effect of I bar. I bar, how do you get it from the formula? 1/36, the base on height, cube, and then you put it here. Divided by y bar, again the same value here, times the area. And you get that, 1 meter. Now let's go back here. You see that? Is IP is 1 meter. So you have a little bit shift with respect to the actual centroid, that is 1/3 of 2. So 2/3. And then you go a little bit below that. You see 1p is greater than 2/3, but you know the coordinate system is from top to bottom. So if you get greater than this, you're below that point. It all depends on what coordinate system. Our coordinate system in our derivation, we took it from the level. So if I get value greater than the centroid, that means I'm below that point. That doesn't mean I'm on top of it, because the coordinate system is upside down. Right? Alright, and that's it. Again, he does, before you solve it, what's the x location of that point? You look at it, it says symmetric, you see that? Compared to the x-axis, you see? It's totally symmetric. You can follow it this way. So you just know x0 is 0. Or you can plug in the formula and you get x0, 0, y, because I x bar is 0. Here, I x bar divided by y over 8. This value is 0. Right? So you get 0. Now, as I mentioned, the next section in your book is using double integral to find the resultant. And the reason that you get that formula, you see this formula, we got it last class. I said you get an element and you get force come from that element. Let me do that to show how it works. This is a general case. If you don't want to use the formula of drives here, you want to use integral. Let's say this is your plate. Now, it's not a straight plate. It's, let's do it two-dimensional plot. See, actually, you have this zucchini. Yeah, because I want to say this is 3D curved surface right here. And this zucchini, if you look it from the side, then you see this face right here that is submerged in the water, and then you have some water. And let's say below it you don't have any forces, so you're kind of like on top of it. Okay? And you want to find the location that this distributed load is acting on. The location that this distributed load, obviously, it goes higher the more you go in, it goes higher. And you know that this pressure force is always in normal to what you are normal. It's normal. Why the force is normal? Do you remember that? Why the force is only 90 degrees? Why? As long as the object is not moving, the object is fixed. Why the force is always perpendicular? Why?
So that all the forces can cancel out, so it stays not moving?
Yeah, but look, when we do FPD, you remember I said, for example, any element here, if you do FPD for that element, you have a normal force and also you have a shear force. Why that shear, the tangential component is zero?
The shear is zero?
Because the shear is zero. You see, this is tau is what? Mu du dy. Do I have velocity for the object?
No.
The shear is zero. Because the velocity gradient is zero. There is no movement. So that's the reason the force component is always 90 degrees. Now if I take an element here, just like that, and there is a P, force acting on, what's the force EF? EF is equal to P dA, just like I did last class, right? So if you take Y location from the top with respect to that element, call it Y, right? What is the X component of that? Is Y times dP, right? Is dF. I'm sorry, the force in Y component. Now, if I want to add all these, it's going to be what? F resultant. So F resultant is what? Integral Y, I'm sorry, moment resultant. Moment resultant is equal to integral Y dP. What should I substitute dP? Y dP is equal to, what should I say dP? dF. dF is equal to what? P dA. So that's the resultant moment. Is equal to resultant force times the location, Y bar. Right? So Y bar times F resultant is moment resultant is equal to integral Y P dA. And what is the F resultant? The F resultant by itself is equal to integral P dA. Right? And what is PDA? PDA is the driver is the relation between the height times gamma H. Right? So each one of these is gamma H. So you get the resultant location Y tilde is equal to integral YP dA over integral PDA. Over the area, obviously there is a double integral. So a double integral is one by double integral. Look, those are these formulas. That's exactly what we did last class. But we simplified that for a geometry like a plate or circle or anything that you have moment of inertia in the handle. So you get this Y thing internal, Y bar plus IX bar divided by Y bar times A. That's all. But in general case, you do the double integral. Now, what I do in the, I'm not going to give this double integral in the test, the actual like Newton one or formalism. But for homework, I'll give you some. So you do some double integral yourself, right? Before we actually go to the next chapter. Next chapter, you don't do double integral, but there's going to be more concepts like continuity equation Right? You need to understand it. You don't do it, but you need to know, understand it all together. Similarly, for curved surface, you do that. In fact, the next example, let's say, if I give you information about this curvature, right? If you have this angle theta, right? So the x component, when you get the resultant force, the x component is going to be sine theta. Y component cosine theta. So you can get component of x and y resultant in the middle by doing the double integral. So the conclusion here is, if you do double integral, you basically can do anything. If you have time to do double integral, you can basically do all these problems. Now, I want to give you a midterm waiver challenge. Right now, we have this problem. So grab a piece of paper. And for this one, we only have 10 minutes.
Oh, thank you.
As you can see, we have, let me do a drawing here. We have a cylinder. This is not a circle. This is a cylinder that is submerged. It's submerged, and this is water. It's totally submerged. So inside that is what? Inside that is vacuum. So you have the water all over it, right? So you have an empty object, the water all over it, and it's submerged to a height, call it H0. So this distance is H0. Right? And the density for water, let's say it's rho W, and the radius, so all information is given, R. So the radius of cylinder given, the height is submerged given, the density of water given. Now the question is says, find the resultant force on this cylinder in both X and Y direction. Now take your X direction, put your coordinate system here, take this as your X, and take this as Y. Just like you did first, right? X and Y. Find the resultant force in X and Y. That means the summation of force on this in X, summation of force on this in Y. Now before we solve it, let's do a little bit of intuitive analysis. What do I mean by summation of force in X? You remember we have 5 steps. System, FTD, and then we write all the equations, and then solve, and then we verify. Now, I know where my system is just this cylinder, right? The empty hollow cylinder. But when we do my FTD, I don't have any loading. I don't see any loading here. Do you see any loading here?
No.
So where do I get that loading from? The loading comes from?
The water?
The water. So if you take an element here, and how many loads do I have? How many point loads? Infinite point loads. You see, if you take anywhere, any element, there is always a normal force. So if you take a circle like that, this is 90 degrees. Why the tangential component is 0?
Because
Because it's not rotating, no moving, so the gradients of velocity is 0, so the shear, which was mu times gradient of velocity, is 0. So you only have normal. And if you look at it from the 2D, you see that's the 2-dimensional plot. How do I do that? I'll just look at it from here. You see that? I'll just look at it from here. So you just see a circle. If you look at this 2D, let me draw it here. There you go. And then this is your X, and this is your Y. For any element, like that element right there, you get this. What do we get in 2D? You get an arc, right? You don't see this side. You don't see the arc with the bottom side. You just see the arc, right? And then you have, I need another color, you have a normal force. And normal force is what? Normal force is PDA. There you go. The normal force is what? PDA. The pressure at that point times the area of that point, the area dA. Yeah.
Would all the summation of x and y be 0 since it's submerged?
Okay.
It's all.
Good point. Let's go step by step. Let's do X. Let's do X direction. What's your gut feeling about the summation of all these forces in X direction? You said 0. You can see that. How can I see that? Well, look at it. This guy, this tiny element is only, well, the distance is always R, right? R is same. We're not integrating over R. R, let's call it R, capital R. R is fixed. But look, I'm rotating over theta. So in every theta, I have a, let's call this d theta. So that's my theta. That's my theta, that's the d theta. At every theta here, I have a d theta, which is an element. And I have a d infinitesimal force. And as he said, you see, if I go the other side, there is always, at the other theta, there is always opposite to that. So when I sum them up in the x direction, you see, if I go to the other side, I have opposite to that. So the x component of both is what?
0.
They cancel out. They're at the same height. So they have exactly the same pressure. So the x component is cancelled out. But what about the summation of force in y direction? Is that 0?
No.
No.
How do you say that even before doing the integral?
Is there different heights?
Because one way is to say, well, you know what, if I have a can that is empty, and if I put it in water, and if I release my hand, what happens? It's gonna go up very, very quickly, right? So there is a force coming from water on it. The resultant force is not 0 in the y, not in the x. It's not gonna go this way, right? It's gonna go to the top. So from just the experiment, you immediately realize that the resultant force in y is what? Non-zero. Another thing you said, we have more pressure here. You see, if I draw the pressure from the surface, it's like linear. Why? Why is linear? Because P at any point was what? Rho G H or gamma H. Alright? So it's proportional to the height of the submersion. So because we have more pressure here, the other force here is not equal to that. It's a little bit greater than that. So y component of that is greater than y component of this. So there's going to be one net y component go up. Now I want to do a Newton waiver here. Give me the value of that y component. So I know this is 0. What's the value of that y component? That's a Newton waiver. It's just summation of all those dF forces in the y component. You see that dF? This guy is just simply dF. The y component of that. What's the y component of that? draw it here, make a better drawing, right? So for the element right here, say this is R, and this is d theta. That force, dF, is equal to what? Pressure times the area. So if this angle is theta from here to here, what is that angle right here?
Sine
Theta.
df.
So y component of that is what?
Sine df. Or
The
sine.
value of force dF times sine theta. Positive or negative?
Negative.
Negative. That's positive this way, right? Positive or negative. So you're just summing that. Sum that. From theta to where to where? Theta from 0 to 2 pi. So sum that theta from 0 to theta to 2 pi. We need more white. Archimedes law, buoyancy. There was an old ancient Greek scientist that he discovered about that if you submerge something in water, there's going to be a buoyancy force on it. Yeah. You want to say something? Right? You want to say something? No?
Not yet.
Not yet. So even if you don't do this double integral, even if you don't do this sum which will convert into double integral, you should be able to tell the answer if you know about buoyancy. Okay, this stuff. That's in fact we are going to drive that mathematically from scratch. One thing that he did it 2,000 years ago. We are going to do it using double integral. I plan to finish that problem today and also do another problem, as you can see here. That's a design problem, but unfortunately, I was a little bit late, 2 minutes late today, and we were not fast enough to cover all this material. So we'll do it next class, but tell me what should I do, what's the next step after that? I'm not really happy, like, I look at some faces are like, this is just a piece of cake, why is he wasting our time? I can tell you. And some faces are like, I'm coming from like Jupiter, like another planet. This is just alien stuff. And I really don't know what way to go. Should I go with the fastest student or with the student that is totally lost here? I don't know really what to do. And these are always the problems all the time in UPC. Some students are really good, some students don't want to practice. So what should I do here? Look.
DF already, right?
Yeah, work on that DF. So DF is what? PDA. Right? You can, for that, you can do PDA. And what can I do for P? Look at the geometry here. The pressure at any surface, I have to go to this water level. Look at water level. Water level is here. You see that? Is the distance between that element all the way to the water level? Not the distance to delta to x. All the way to water level. So what can I write for that h?
H0 minus the distance.
Yeah, h0 minus this distance, right? So look at it. The water level is here, right? And I know from here, this space to water level is h0. And what I need is from here to here. this is what I need you to put into pressure, this H. What can I write for that H? H is equal to H0 minus this distance, right? And what is that distance?
What?
Which is, look at this triangle.
Sounds.
Yeah, R sine theta. So H0 minus R sine theta is I put here. So for P you put gamma H0 minus R sine theta. Rho G H. And then you multiply by dA, which is basically that's your dF. That's it. Now put it all together, what do you get? You get negative for dF, you get gamma H0 minus R sine theta. Gamma, so let's do negative gamma H0 minus R sine theta. And then dA is just root dF. And there's going to be another sign on top of that, so I'll put it here before dA. Sine theta, dA, not d theta, dA, right? And then sum from theta to 2 pi. What is that sum? It just said integral, right? From theta 0 to theta 2 pi. That's my sum force in y. Resultant. Resultant in y. What do I get for that? How do you evaluate the integral?
0.
Do it at 2 pi and then minus doing it at 0.
Yeah, look. This one, the integral is over theta only. There is no double integral. Why? Because my radius is what? Always fixed. I'm just looping over the surface of this cylinder, right? Not the body, not inside the depth of cylinder. So R is 0, so theta from 0 to pi. Now this integral, if you evaluate it, what do you get? What should you get for that?
0.
It's not 0 because if I put my can in the water, what happens? It's gonna go on. It must not be 0. If it's 0, something wrong. You know, what I really expected you guys to know, at least the law of buoyancy.
You get the
You know,
buoyancy
it
force.
wasn't in the high school like, no, you didn't study like, nothing at all to do. Like Wikipedia, YouTube, nothing, never watched any science videos.
I've heard of it.
Heard of it.
I mean, a long time
But
ago.
never
Okay, so,
studied.
no problem, let's do this, next class, we will, before we do next class, do this at home and send it to me, okay? Email it to me. Let's do a homework. So I do homework before the next class, this is your next class, before the class. Do this integral at home and I'll put it in the homework section. Just one problem, one question. And then next class I'm gonna do it, and then I'm gonna bring some videos from YouTube, show the law of Archimedes, the law of buoyancy, and then you can compare their exactly. And then we go next section. Now, it is a little bit slow.
Wednesday's next class is right. Yeah. I wonder where we're going Wednesday.
I don't know.